Welcome back to the deep dive. Ready for another deep dive into the OEIS?
Always.
This time we're looking at A000083.
Oh, this one is fun.
It seems to pop up in a bunch of different areas of math.
Yeah, it's kind of like a numerical chameleon.
Oh, okay. Like a chameleon.
Yeah, it sort of blends in and appears in these unexpected places.
So where do we even begin with this one?
Well, the sequence itself is 1, 1, 1, 2, 4, 9, 23, and so on.
Okay, and what makes this so special? What kind of math are we talking about here?
Well, that's the interesting part. It has these two pretty different interpretations.
Okay, so less like a chameleon is more like a bridge connecting two different things.
Exactly. On one side, we have something called mixed Hosoya trees.
Hosoya trees, I've heard of those. Aren't those from like statistical mechanics?
Right. They're used to model things like how particles cluster or how polymers form.
Okay, I'm vaguely remembering those tree-like diagrams. So what makes them mixed?
Mixed basically means the branches of these trees can have different types.
Types like what?
Well, it depends on the context, right? But imagine different types of forces or bonds.
Ah, okay. So the mixed part adds another layer of complexity to these structures.
Exactly. And the sequence A000083 is counting the number of ways you can arrange these different branches.
So as you add more nodes to the Hosoya tree, the sequence tells us how many possible arrangements there are.
Precisely.
Okay, so that's one side of our numerical bridge. What about the other?
On the other side, we've got, well, cacti.
Wait, cacti, like the prickly desert plants.
Yeah, but in this case, we're talking about polygonal cacti with bridges.
Polygonal cacti with bridges. You've got to be kidding me.
It's true.
Math is a lot weirder than I thought. But okay, cacti. Help me understand this.
So cacti in this context refers to cactus graphs.
Okay, so we're not talking about actual cacti. What are cactus graphs then?
Well, a cactus graph is a special type of graph where any two cycles share at most one vertex.
Cycles, like loops.
Exactly. Think of it like a chain of connected loops. But these loops aren't just circles, they can be polygons.
Polygons, like triangles, squares, pentagons, and so on, all linked together.
Yeah, exactly. Now imagine connecting those different polygons with bridges.
So the bridges are like the edges connecting those polygons.
Yes.
Okay, I'm sort of picturing it. We're linking together these different shapes with bridges to create these branching cactus-like graphs. But this is where it gets really crazy, right?
What do you mean?
This same sequence, A00000083, that's counting our mixed Hosoya trees. It's also counting these polygonal cacti with bridges.
It is.
How is that even possible?
That's the really fascinating part. It suggests a deeper connection between these two ideas.
Okay, so it's more than just a coincidence that these two are counted by the same sequence.
Right. It hints that there are some underlying principles that govern how complex systems are organized, whether those systems are particles in a polymer or nodes in a network.
So we're seeing this unexpected link between something in physics and something in graph theory.
Exactly. And it makes you wonder what other connections we might be missing.
Right. Like how much more is there that we just haven't figured out yet? But before we get too philosophical, let's try to unpack some of the details here.
Okay, sure.
The OEIS entry for A000083, it mentions something called generating functions, or GFS.
Oh, yeah.
Could you explain what those are in, relatively simple terms?
Well, a generating function, it's basically like a mathematical blueprint.
A blueprint?
For what? For sequence. Like, imagine a machine that spits out the numbers in our sequence one by one.
Okay, I can picture that.
The generating function is like the blueprint that tells you how that machine works.
So instead of listing out 1, 1, 1, 2, 4, 9, and so on forever, we have this formula that represents the whole sequence.
Exactly.
Okay, that makes sense. But why is that so useful?
Well, it turns out that by manipulating this formula, you can sometimes uncover hidden relationships and patterns.
Patterns that you might not see just by looking at the numbers themselves.
Okay.
So it's kind of like having a secret decoder ring for the sequence.
Then,
so what does the generating function for A000083 tell us? Does it give us any insights?
It does. This particular formula is interesting because it links the generating function for our sequence to the generating functions of 3 other sequences.
Wait, 3 other sequences?
Yeah, A000237, A035349, and A035350.
So it's like our numerical bridge is actually part of a bigger network of sequences.
Exactly.
But what are those other sequences? What do they represent?
Each one represents a different type of graph structure.
What?
And the formula shows how those 3 sequences kind of like combine together.
Like ingredients in a recipe.
Yeah, exactly. To create our sequence, A A00000083.
Okay, so we've got this interconnected web of sequences, each describing these different structures, but somehow they're all related.
It's pretty wild, right?
It is.
Yeah.
But I think we need to step back for a second and think about what all of this means.
What do you mean?
Well, we started with these concrete things, right? Yosemite trees, polygonal cacti, we could visualize those.
Yeah.
But then we went to this abstract level with sequences and generating functions.
Okay.
What's the big takeaway here? What are we actually illustrating?
Well, I think it shows the power of abstraction, right?
Yeah.
We started with specific examples, but then we stripped away those details and arrived at this more general concept.
So we're seeing beyond the surface differences to the underlying mathematical structure.
Exactly. And that's one of the most powerful things about math. It allows us to find these universal truths that apply across different fields.
Okay, I think I'm starting to get it. So we've talked about these two interpretations of A00000003, but the OEIS entry also mentions some real-world applications.
Oh, yeah.
Yeah, it mentions things like representing electrical circuits
Oh, right.
and comparing genomes. How does that tie into all of this? I'm having trouble picturing how that works.
It's a bit tricky to explain without getting into the details of graph theory,
Fair enough.
but the basic idea is that cactus graphs can be used to model certain types of networks.
Like circuits and biological systems.
Yeah, those are a couple of examples. The structure of the cactus graph can capture some of the essential properties of those networks.
Okay, so we're seeing that even though we started with this purely mathematical concept of a sequence, it actually has some connections to the real world.
Right, and that happens a lot in math. These abstract ideas end up having applications in unexpected places.
It's pretty amazing when you think about it. We haven't even talked about everything in the OEIS entry for A000083.
There's always more to explore.
Right, like it mentions triangular cacti and something called Rose's conjecture.
Oh, yeah.
Can you give us a quick rundown of what that's all about?
Well, triangular cacti are a special type of cactus graph where all the cycles are triangles.
Okay, so every loop in the graph is a triangle.
Exactly. And Rose's conjecture is this unsolved problem in graph theory.
Oh, an unsolved problem.
Yeah, it has to do with labeling the vertices of these triangular cacti.
Labeling them, like assigning a number to each point.
Right, there's a specific way of labeling them called graceful labeling.
Well, and what does Rose's conjecture say about that?
It says that all triangular cacti are either graceful.
Meaning they can be labeled in this special way?
Right, or they're very, very close to being graceful in a certain way.
So we're still not sure if the conjecture is true.
It's still an open question. Mathematicians have been working on it for decades, but nobody has been able to prove or disprove it.
So it's a real mystery. And solving it could have big implications for graph theory.
Definitely. It would give us a deeper understanding of these structures.
I love how even within this world of cacti and sequences, there's still these unsolved problems.
It shows you that math is a living, breathing subject.
Always evolving.
Right. And there's always something new to discover.
Well, I think that's a great note to end on. We've journeyed from the microscopic world of particles to the complex realm of networks, all guided by this one intriguing sequence.
And we've only just scratched the surface.
Right. So to our listeners, I encourage you to explore the OEIS for yourselves. You never know what amazing patterns and connections you might find. Until next time, keep diving.